Okay guys, so today I want to make a video, a very straightforward video about Lagrangians and their applications to systems like pendulums and various examples. So a very good problem is this. We have a circle. Oops, sorry. And then there's a block. We have a table first of all. And then there's a block on this table. And there's a hole in the table. And then the block is exhibiting circular motion, let's say M1. And then through the end of this circle, this hole, comes out mass 2. And let's assume that M2 is greater than M1. And equations of motion. That's the problem. Let's do it. So, Newtonian, how would we do this in Newtonian mechanics? I'm going to show you the stark contrast between Newtonian mechanics and Lagrangian mechanics with this clear example. So, and the string has length L. So, if this is R, right, then this portion over here, since the whole thing is L, this portion has to be L minus R, right? Because when you add them up, they have to equal L. Okay? Now, okay, Newtonian. How do we do this Newtonian manner? So Newtonian, we would get all the forces and set them equal to ma. So let's look at block number 2. M2. What do we have? We have a M2G. And upwards we have a tension. Fairly simple. And block 1. We have this going on, M1. We have a tension towards the radial direction. Let me draw that a little better. And let's say this is theta. Okay, so this will be theta right here, right? Yep. Okay, and then we can break this up into components, yada yada yada. So let's do it. So for this we have T minus M2G, that's the force, is equal to M2. And now it's A. Well, this is the Z direction, right? And the upwards direction is the Z direction, right? Because we're working in 3 dimensions here. So B is equal to double dot. Okay? And for this one, we can look at both components, the tension in the radial component and the tension in the vertical component. Okay, so tension is only in the radial direction, so T is going to be equal to mv squared over r. Okay, and then in the radial direction, sorry, this is not quite right. And that's the big thing here, because this is wrong. Why is this wrong? Well, and this is actually a common misconception. Right? Many people think that v squared over r is a centripetal acceleration, but it's not. Now this might be very, very surprising to you. All your life, all your physics life, you've been thinking this. No, it's not right. And I'll tell you why. And to show this drastic difference, we're gonna have to go to polar coordinates right here. So in polar coordinates, let's say we just have a circle. Okay? And the mass, and it's orbiting with an omega. Right? And we have r and theta. Okay, so what do we have here? We're gonna have that the position is just gonna be r, right? Oops, sorry, I used little r. There's just gonna be little r, the radius, in the theta direction. And I'm gonna use r hat, just to make it very appealing, right? It's gonna be r in the radial direction. And then the velocity is going to be the derivative of this, right? And this is just a chain rule. What do we have? We keep r, and we take the derivative of r hat, and then we add r hat, and we take the derivative of r. What's the derivative of r? It's r dot. Okay, and what's this term over here? Well, you can do some geometry, but you'll find out that r hat dot is just theta hat. Okay, so sorry, not theta dot. It's gonna be theta dot in the theta direction, right? You could just figure this out from the geometry, right? So what is this gonna equal? This is just, we substitute it, so we get r theta dot in the theta direction and r dot in the radial direction. And this, if you're familiar, is r omega. Theta dot is just omega. So this is the linear, the tangential velocity, right? You know that the velocity in polar coordinates is going to be tangential because it's in the theta direction. That's where it comes from. Now, you notice that there's another term here. What is this? Velocity, you're taught, has only one component in polar coordinates. That's in the theta direction. But there's actually a component in the radial direction. What's r dot? R dot is dr dt, the change in the radius. So normally we think that the radius doesn't change, right? The radius is fixed and you're just going in uniform circular motion. But the radius can change. The radius can get bigger if you're expanding, and the radius can get smaller if you're decreasing. So there's going to be another term here, right? But we're so used to setting this equal to 0 that that teachers don't even teach this anymore, because we're so used to setting it equal to 0. But that's not the case. R can change, and that's a very important point. Okay, so that's our velocity, and one more time, we're going to have our acceleration. So this is going to be the derivative of r theta dot in the theta direction plus r dot in the r hat, right? This r dot is very important. So what this is going to be, this is going to be a chain rule again. I'm just going to tell you the answer. So let me see. So our double dot, the acceleration is going to be, from my notes, you don't have to memorize this. Well, actually, yes, you do have to memorize this. You don't have to memorize the derivation. You just have to take the derivative, right? This is going to be a triple product rule, and this is going to be a double product rule. It's just a lot of math. So in the end, this is what we get. We get r double dot minus r theta squared in the radial direction, sorry, r hat, plus r theta dot double dot plus 2 r dot theta dot in the theta direction. Okay, so this is the acceleration of a system moving in polar coordinates. Very important. Now notice. This is the full acceleration, taking into account that the radius can change. Radius can change. It's possible. And an example that we have, right? The radius is changing. It's getting smaller. So think about it. If the radius is constant, it doesn't change, then we just have this term. And notice this term, it's m omega squared. And what's m omega squared? It's just mv squared over r. This is the centripetal acceleration that you think. But the centripetal acceleration is actually r double dot minus r times v squared. Oh, sorry. Oh, it's not mv squared, it's just v squared over r. So that's the actual centripetal acceleration, taking into account the change of the radius. That's very important to know. Okay, so now let's get back to our problem. So, Newton says we sum the tension in the radial direction, right? So what is this going to look like? It's going to be tension equals R double dot, and we have an M1. R double dot. Oh, actually, tension is in the negative direction, right? Because if this is the center of the circle is going radially outward, and this is going radially inward, so it's minus tension. Okay, so minus tension is mass times acceleration, centripetal acceleration, and we just said what centripetal acceleration right here is gonna be R double dot minus R omega squared, or R theta dot squared. This is the actual formula. Okay, and now in the tangential acceleration. In the tangential acceleration, right, that's this way, in the theta direction, there is no force, so it's just 0. So 0 is m1 times the acceleration in the tangential direction. And in the tangential direction is this term over here. Now notice this term is r alpha. R alpha is the angular acceleration. But now we have this term that changes if the radius changes. And there's a specific name for this term. It's called the Coriolis force. I bet you never learned that, because you're so accustomed to setting this equal to 0. This term is actually called the Coriolis term, Coriolis force. It's pretty crazy stuff. So let's put that there. 0 is equal to m1. Whoops, my pen is spazzing. Times this r alpha plus the Coriolis term. I'm not sure about the derivation of this, where this Coriolis name comes from, but I'm assuming it has something to do with the Coriolis effect. So that's one equation, that's two equation, and then this is our third equation. And now Newton says that we must have some constraint, and clearly our constraint is very easy to find here. Our constraint is that, well, the string has to have a length of L, right? So that means that R, the length of this, plus the length of the vertical direction, which is Z, has to be equal to L, right? Very simple. If you add the Z length of the string and the R length of the string, you have to have L. It has to be constant. So if we take the derivative of this twice, the derivative of L is just 0. So we get R double dot plus Z double dot is 0. Or if you want to write it more compactly, Z double dot is negative R double dot. And we can plug this in here. So lastly, we're going to get that the tension minus M2G is equal to minus M2R double dot. So now notice, we have tension we don't know, we have R we don't know, and we have theta that we don't know. 3 equations, 3 unknowns. You can solve for everything now, right? It's very simple. But, you know, constraints, force diagrams, there's a lot of possibility to mess up here. So, we turn to our buddy Newton. Sorry, not Newton, Lagrange. We turn to Lagrangian dynamics. We have the same diagram. Let me draw this first. Let me draw it a little bigger. Okay. Okay, and This is the z direction, positive z. Okay. So, Lagrangian dynamics. Lagrange. Now with Lagrange, this makes this problem so easy, it's basically trivial. Okay, what does Lagrange say? Well, Lagrange, we have to find the kinetic energy of the first term and the kinetic energy of the second term. So the kinetic energy of the first term is just 1/2 m1 x dot squared plus y dot squared. And we can use some polar coordinates here, right? We use coordinates that are convenient to us. So our qi is going to be just the polar coordinates. It's going to be r and theta. And I'm sure you know this, x equals r cosine theta, and y equals r sine theta. Just to reiterate, we're using polar coordinates here because we have circular motion. It's convenient for us. So our generalized coordinates are just going to be r and theta. So we take the derivative, x dot is, this is product rule, so we keep the first term, and we take the derivative of cosine, and then the second term, and then we take the derivative of y, same procedure, plus product rule, and then that's it. Now we have to square it. So t1 is 1/2 m1 x dot squared. What is this going to be? First term is going to be r squared sine squared theta, theta dot squared, plus cosine squared theta, r dot squared, and then we have an overlap minus r sine theta, cosine theta, theta dot, r dot, and then we have the second term plus r squared cosine squared theta, theta dot squared, plus sine squared theta, r dot squared, plus, and then the overlap r sine theta, cosine theta, theta dot, r dot, right? Just expanding it. And now notice that this cancels out with this, right? And notice, what else? This is going to simplify, and this is going to simplify. So we're just left with this, right? Why does it simplify? We have sine squared theta, and then we have cosine squared theta. So it's just going to be r squared, theta dot squared, and the same thing here. Sine squared theta plus cosine squared theta. That's just Pythagorean theorem. So we just have this. Great, we got T1. T2, very easy. T2, it's only in the z direction, so it's just 1/2 m2 z dot squared. But what's z? Well, we know that L plus R is, we know R plus Z is L. So Z is just L minus R. Very simple. We didn't have to take any derivatives. We just have the length. So it's just 1/2. Oh, and then we take the, I lied. We just take the first derivative. It's going to be negative R dot. 0. Okay, so we plug that in, 1/2 m2 z, z dot is negative r dot, so that's just r dot squared. Okay, and now we're done. We have and v1. The potential energy of the first one, well, it's in the plane, so it has no potential energy. If we have to set our inertial reference frame. So if our inertial reference frame is the origin, we can draw a coordinate system here. Right? Oops, let me draw that a little better. This is y, this is x, and this is z. Hopefully you can visualize that, right? This is going to be a right angle. Z is up, y is this way, and x is that way. So what are we going to have here? Oh yeah, if we call this the origin, then the potential energy is 0. So that. And then v2 is just going to be m2 times g times z, which is, and z is equal to L minus R. But it's below It's below the origin, right? If we set the origin equal to here, so it's just going to be below here. So minus m2g times L minus R, which is equal to m minus m2gl plus m2gr. Okay, very simple. And now we construct the Lagrangian is t minus v. What is it going to be? Well, we have this term, 1/2 m1 r squared theta dot squared plus 1/2 m1 r dot squared plus 1/2 m2 r dot squared, and then minus this, so it's going to be plus m2gl minus m2gr. Great, we got the Lagrangian. Now what can we do? Well, we're working this basis of r and theta, right? So we're going to have two equations of motion. So the first one, very simple, dl dr equals d dt dl dr dot. What is this going to yield? What's dl dr? We have an r here. So take the derivative, which is going to be m1 theta dot squared r, and take the derivative here. This is going to be minus m2g equals, and then we have to take the time derivative of dl dr dot. So we have two terms, 1 and 2. So this is just going to be m1 r dot plus m2 r dot. I hope you can see that. And simplifying a bit more, the time derivative is just m1 plus m2 times r double dot, right? Because it's just a derivative, and then I factored everything. So that's our first equation of motion. And then the second equation of motion, fairly simple again, is just going to be dl d theta, that's our second basis, is equal to time derivative of dl d theta dot. Okay, so dl d theta, oh, there's no theta, so that's just 0. Nice. So 0 is equal to the time derivative of this, which is just going to be m1 r squared theta double dot. Oh, sorry, no, it's not. It's not going to be that. It's going to be the time derivative, I forgot the time derivative, of dl d theta dot. So theta derivative is going to be m1 r squared theta dot. And then we take the derivative, it's just going to be, we bring the m1 outside. So this is just chain rule, 2r r dot theta dot plus theta dot, oops, plus r squared times theta double dot. And we can factor an r, so we get m1r times, right, we just factor this outside, and we factor one of these outside. So 2r dot theta dot plus r theta double dot. That's it. Those are the equations of motion for our system. Now, notice, what does this term look like? This is the tangential acceleration, right? This is the Coriolis force, and this is the regular one that we know as r alpha. This is the tangential acceleration. We've derived Newton once again from Lagrange, but we've gained another insight. Man. Now, this is the same exact solution, except we have two equations, and it was much easier to do it. You didn't have to pick any forces, you didn't have to do anything. You just have to make the kinetic energy and the potential energy. Very simple. Okay, and now I want to show you one more thing, and that's it. It has to do regarding pendulums. It's also something that you haven't learned yet. So I've already showed you that what you're learning with centripetal acceleration is all flawed, right? And now I'm going to show you what you're learning with pendulums is also flawed. So let's consider the most general case of a pendulum. The most general case, right? We have a pendulum that goes into 2 dimensions. That's very specific. We have a conical pendulum that's also very specific. We want to consider a pendulum that's just going in 3 dimensions. That's the most general case. So a pendulum going in 3 dimensions will look something like this. It's gonna have an R, and then it's gonna go in some kind of orbit. It's gonna go in some kind of trajectory. Right? We don't know what this is, and it's gonna have phi. Okay, that's what it's gonna look up. And this angle can be a right angle. So try to visualize that. This is not a conical pendulum. This thing can go in the z direction. It can go up. In a conical pendulum, the mass is constrained in the 2D plane. Imagine that this mass is going up and down, like a sine wave. Imagine it could go anywhere, like a chaotic motion. Okay? Imagine that this is free to travel in any 3 dimensions, right? We have x, y, and z. Imagine it's free to travel in any direction. This is the most general case. Okay? So now, let's consider it. What's the equation of motion? Very simple. We have t equals 1/2 m. Now we have x dot squared plus y dot squared plus z dot squared, which is equal to, okay, first we have to figure out x and y and z. X is just, and let's say this is L. So x is r, again from polar coordinates, r times the cosine of, not theta, of phi, right? Because phi is in the plane. Phi is in this 2-dimensional thing, while theta is the angle from the ceiling, from the z direction. Y is r sine of phi. And what's z though? If this is L, then we just use Pythagorean theorem, right? This is a right angle, so it's going to be L times cosine theta. Okay? And if this is L cosine theta, we know R is L sine theta, right? It's just the opposite. So this is going to be okay, so R is L sine theta, so this is going to be L sine theta times cosine phi. It's going to be L sine theta, right? I'm just substituting for R, times sine of phi. And this is going to be just L cosine theta. See how easy that was? That's it. Now we just take the derivatives. X dot is going to be, I'll spare you some of the calculations. I have it written over here. X dot, where is it? Oh no, where is it? Well, I don't have it. Okay, let's do the oh, here it is. Okay, sorry. X dot is going to be negative r sine theta times theta dot plus cosine theta. Wait, what am I doing? This is not it. Alright, I guess we're going to have to do this by hand. Okay. X dot. L is pulled outside, and we have sine theta, negative sine theta, because product rules. Sine phi, phi dot, plus cosine phi, cosine theta, theta dot. Okay, y dot is L. I'm just gonna fast forward this for you. Okay, so I spared you some of the gory details in this calculation. You can pause this video and try it for yourself, and then compare your answers with mine. Okay, so this is x dot, y dot, and z dot, and then I squared them to get these expressions, and then everything simplified in the end. We have a lot of Pythagorean theorem and whatnot, and this is the final expression: 1/2 ml squared times sine squared theta, phi dot squared plus theta dot squared. It's just a lot of calculation, but it's very easy to do if you don't mess up. And now the potential energy is going to be mgz which is just, well, we have to set up an inertial reference frame, right? So again, we're going to say this is our inertial reference frame. This is our origin. So it's just going to be minus, so this should be minus mgl cosine theta, right? Because z is going to be below the x-axis. Unless we have an inverted pendulum. And that's going to be another story. Okay, so then we can set up our Lagrangian. It's just going to be 1/2 ml squared sine squared theta phi dot squared plus theta dot squared plus mgl cosine theta. Very simple. Okay, we can expand this a bit. We get 1/2 ml squared sine squared theta phi dot squared plus 1/2 ml squared theta dot squared plus mgl cosine theta. Very simple. That's our Lagrangian. I'm not even gonna box it. Now, what's our basis? Our generalized coordinates are just theta and phi. So, that's it. Let's go. Now we just do the Euler-Lagrange equations. So the L d phi is the time derivative of dl d phi dot. What does this give us? Phi. There is no phi in here, so it's going to be 0. So 0 is equal to the derivative of that. So it's going to be ml squared. Sorry. It's just going to be the derivative of ml squared sine squared theta phi dot squared. Phi dot, sorry. Okay, so if the derivative of this is 0, that means that this has to be a constant. Right? You can do that with everything that's derivative is 0. Right? Because why? Why is that? If this is a constant, say this is 5, then the derivative of 5 is just 0. So that means that ml squared sine squared theta times phi dot is a constant. What do you want to call it? You can call it h. And this is also a constant. So if we divide, we just get that sine squared theta phi dot is h. It's just a constant. Right? Because we're dividing by a constant, so we get rid of this constant. This is a constant, and then we just get that. Okay, that's the first equation of motion. And then we have one more. dl d theta equals the time derivative of dl d theta dot. I'll spare you some of the details of the calculation, and I'll just write the results. Theta double dot plus g over l sine theta minus sine theta cosine theta phi dot squared is 0. If you do the calculation, you'll see that this is the answer. Very simple, you just take the derivatives. Oh, I can't draw boxes today. One more time. There we go. So now, we have 3 different cases here. As I said in the beginning, this is the case for a general spherical pendulum, like 3D. So now we look at the cases. Alright, case 1. Case 1, we want to look at just a regular pendulum. And in a regular pendulum, notice that, where's my diagram? Where's my diagram? Here it is. Okay, now notice in a regular pendulum. The pendulum, in a regular 2-dimensional pendulum, it only goes back and forth. So it only goes like that. Back and forth. In a 2-dimensional plane. So if it goes back and forth like that, then this angle here, it doesn't change, right? If it would change, then it would be a conical pendulum. So if it goes back and forth, that means that phi is constant, right? If it's constant, then it'll just go in this plane, like a regular pendulum. So case 1 is the case when it's constant, when phi is constant. phi equals constant. So now, as we did in this case over here, the derivative of phi is going to be the second derivative of phi, 0. Right? What's the derivative of constant? 0. So what are we going to get here? Equations of motion. This term is going to cancel out because phi dot is 0. So we just get this. This is the equations of motion for a pendulum, a two-dimensional pendulum. Now notice, this is the big picture of everything that I have done right now. In school, in whatever class you're taught that the equation of a pendulum looks like this, right? You're taught that its theta is equal to A cosine omega t, where omega equals radical g over L. And you did this by solving this solution is a solution to this equation. Solution to this equation. That's a solution to this equation. But notice that here we have a sine of theta instead of a theta. And so here we come to the conclusion. For small angles, sine of theta is approximately theta. That's how you get from this equation to that equation. You assume that the angle is small. Because if you want to solve this equation, it's nearly impossible. Okay, you would have to go into some kind of Jacobian amplitude functions and elliptical orbits, and elliptical functions. So, in the solutions that we use, in physics, we assume that there's a small angle. Now, no one tells you this. No one tells you this. That's why you can't find the equations of motion for a pendulum that starts out at 90 degrees and then goes down. You're going to have to use conservation of energy. This equation is only for small angles. And that's the big picture here. And you were never taught this, and I don't know why. It's very important. This equation is for small angles. Well, this is the general equation of motion. Okay, and we have one more case. Let me just do it over here. It's very short. Case 2. How can we get a conical pendulum? For the case of the conical pendulum, this thing is, phi is now changing. For the conical pendulum, we're just moving in a circle, right? In a circular orbit. So theta is going to be fixed. Right? If we're moving in a circular orbit, then theta doesn't change. So theta is a constant now. Theta equals constant. Conical pendulum. So if theta is a constant, let's look back at this equation. This is going to be 0, and that's it. So what do we have? We're just going to left with g over L sine theta equals, I'm going to bring this to the other side, sine theta cosine theta phi dot squared. Sine theta cancels out, and then we solve for phi dot. Phi dot is just radical g over L secant theta. And there we go. This is the angular, and it's omega. Right? Phi dot is just omega. This is the angular speed for a conical pendulum. And trust me, it would take you 45 minutes to derive the angular speed for a conical pendulum using Newton's laws. And see, we derived Newton, once again, from Lagrange. Thank you very much.